Okay, this is a high AP chemistry class. This is Mr. Mellinger, and this is your video lecture for 8th, 2019. We're still on solutions. We're going to do some reading today and a few short problems, not the extensive long problems like we had yesterday. Okay, so we're going to read along and here we go. The solution process. The energy is involved in solution formation. When a solute is dissolved in a solvent, the attractive forces between the solute and the solvent particles are great enough to overcome the attractive forces within the pure solvent and within the pure solute. The solute becomes solvated, usually by dipole-dipole or ion-dipole interactions. When the solvent is water, the solute is hydrated. So when you throw salt into water, the attraction between a water molecule and one of the chlorine ions or a water molecule and one of the sodium ions is stronger than the sodium and the chlorine have for each other. And so that creates a dipole, an ion-dipole interaction, and the water molecule pulls either the sodium or the chlorine away from the salt crystal. Those substances with similar types of intermolecular forces dissolve in each other. Like dissolves like. So it's very important to remember that polar solvents dissolve polar or ionic solutes. They're basically magnetized. Non-polar solvents dissolve non-polar solutes. They don't have any permanent dipoles, and so it's only the London dispersion forces that cause them to interact with each other. Water dissolves many salts because the stronger ion dipole attractions water forms with ions of the salt are very similar to the strong attractions between the ions themselves. The same salts are insoluble in hexane, which is a nonpolar molecule, because the weaker London dispersion forces their ions could form with this nonpolar solvent are much weaker than the attraction between the ions of the salt. So you throw salt into hexane, and the sodium and the chlorine attraction to each other, those two ions, positive and negative, have a stronger attraction for each other than either of them has for the hexane, which is nonpolar, and therefore salt does not dissolve in a nonpolar substance like hexane. Oil does not dissolve in water. Oil is immiscible, doesn't mix with water. In water, due to the fact that any weak dipole-induced attractions, that means London dispersion, that does not mean London dispersion, dipole-dipole attractions that form between the oil and the water cannot overcome the stronger dipole-dipole hydrogen bonding that the water molecules have for each other. Solubility of alcohols in water. As the hydrocarbon portion of the alcohol increases, that means the nonpolar portion, in length, the alcohol becomes less soluble in water because it becomes more nonpolar. More of the molecule is nonpolar, the dipole moment is diminished. Okay, the solubilities of alcohol in nonpolar solvents, as the hydrocarbon portion of the alcohol increases in length, the alcohol becomes more soluble in a nonpolar solvent such as hexane, and therefore it will dissolve. An alcohol will dissolve in a nonpolar solvent. Enthalpy of solution. The enthalpy change associated with the formation of a solution is just the sum of the steps involved. So the next page will go through those. So the enthalpy of formation, by the way, that circle with the little X is when I changed from a PDF file to a Word file, just a little, the delta, which is a triangle, turned into that little circle with an X, and I didn't catch that. So that's basically a delta. It's change in H of solution equals change in H1, delta H1 plus delta H2 plus delta H3. Remember, delta is that little triangle. Okay? So the delta H solution, positive, endothermic, or negative. So when you mix something into a solution, it can either take in heat when you do that, or it can give off heat during that process. And what the graph is showing on the right-hand side of the page there is you start with, well, anyway, let's go to the explanation on the next page, okay? Okay, so here are the 3 steps of forming a solution, and they're very logical. When you think about them, they make sense. Okay, so the delta H1, the change in H1, that's separating the solute into individual components of the solute. That's called expanding the solute. So in other words, you take the salt, the table salt, sodium chloride, NaCl, and you break it into a positive sodium cation and a negative chlorine anion. You break that salt molecule or whatever the solute is up, and that's step 1. That requires that you add energy. It takes energy to break something. So energy is added to the system. That means the step 1 process is endothermic. It takes in heat. The magnitude of the value is high in an ionic or polar solute and low in nonpolar solutes. That's because polar and ionic solutes hold each other together with stronger intermolecular forces or stronger bonding. So it takes more energy to break them apart. Okay, so the delta H of the solute is equal to the delta H of the lattice energy. That's basically just the energy to break it up. Okay, step 2. The change delta H2, overcoming the intermolecular forces in the solvent and making room for the solute. So if you have a bunch of water molecules together and you throw salt in them, the water molecules, which are attracted to each other by dipole-dipole forces, are going to have to be pushed apart. So that's called expanding the solvent. And that requires that energy also be added. It takes energy to push things apart. And that's also an endothermic process. The magnitude of the value is high in polar solvents and low in nonpolar solvents. And finally, the step 3, this is putting it all together, the interaction of the solute and the solvent. That's when the solute, the water, and the ions come together in the case of salt water to form the solution. The energy must be released here, else the solution would never form, since nature always tends toward a lower energy state and is thus exothermic. If all 3 states required that you put in energy, it's a reaction that wouldn't take place, because molecules and atoms are lazy. They want to go to lower energy states, and so there has to be a lowering of the energy, and this is where it takes place. The magnitude of this value is high in a polar solute, polar solvent interactions, low in other types. Again, anything that's polar is held together by stronger forces and therefore takes more energy in, also lets more energy off. Okay, so steps 2 and 3 are called the enthalpy of hydration. In the case of water, that means you're adding water to the solute, and that's called the enthalpy or heat of hydration. Okay, enthalpy of hydration is more negative for small ions and highly charged ions. Okay. Okay, let's take a look at this table. It's a little hard to read because I guess the NIMSY people made this some kind of a photocopy out of a book, so a little hard to read, but let me read it for you. It's basically giving you the four possible combinations of polar, nonpolar. So if you have a polar solvent and a polar solute, those are going to dissolve. That's salt in water, for example. It's a large delta H1, delta H2, that is to get the salt in the water to break up, and a large delta H3, that's when they come together, that gives off energy. The overall delta H of the solution is small, but the delta H is negative. That means heat comes out, it's at a lower energy state, and so the outcome is that a solution forms, an actual reaction takes place. Okay. If you look at the second one, it says a polar solvent and a nonpolar solute. Now, we've already just learned that doesn't happen. Okay, so it doesn't take much, since it's a nonpolar solute. It doesn't take much to break up the solute because it's nonpolar. It's easy to break it apart, but the solvent's hard to break apart. So the delta H of the delta H3, that's the amount of energy it's going to give off, is small. And what you end up having is the delta H of solution is positive. That means the overall reaction to do this takes energy in. Well, nature doesn't like to take energy in. A chemical reaction is not going to take place if it increases the energy after the reaction takes place. And so this reaction won't take place. So it says on the right, no solution forms. So polar, nonpolar doesn't work. Okay, nonpolar solvent, nonpolar solute. So that's alcohol, throwing alcohol into a hydrocarbon or vice versa. The bottom line is this. The delta H of solution is small. It is negative. That means heat comes out. So a solution forms because it ends up in a slightly lower energy state. And finally, the last one is a nonpolar solvent in a polar solute. That's throwing alcohol into water, for example. It's a large positive delta H of solution. That's the next to last column. That means the whole process takes energy in. Well, nature doesn't like a reaction where you have to put energy into it. It wants to end up at a lower energy state, and therefore no solution forms. So the bottom line of all that table is just that polars mix with polars, nonpolars mix with nonpolars, and the other way it doesn't work. Okay, so some heats of solution are positive endothermic. The reason that the solute dissolves is that the solution process greatly increases entropy disorder, which overrides the cost of a small positive heat of solution. Okay, this entropy is part of a area of chemistry called thermodynamics, which we haven't covered yet. It's basically a force that works against the idea that you want a lower energy state. It's something that could actually work against that and make the reaction go in the other direction. We'll talk about that when we get to thermodynamics. Hot packs, cold packs, we're going to skip that. Okay, here's a short problem. On page 8, decide whether liquid hexane C6H14 or liquid methanol CH3OH is the more appropriate solvent for the substances of grease, C20H42, and potassium iodide, Ki. Okay, well, you can already see the answers down there in the corner, but why? Okay, well, hexane is a hydrocarbon, and hydrocarbons are nonpolar. Okay, if you look at the grease, it's also hydrocarbon, it is nonpolar. So both of those are nonpolar, so those two will dissolve in each other, hexane and grease. Okay, all right. The liquid methanol, now you may not be sure if that's polar or nonpolar, but just by looking at the formula, you can see that it's what I would just call a lopsided molecule. It doesn't look symmetrical, right? It's got 3 H's over by the C, and then it's got an oxygen, and then it's got a hydrogen sticking out of the oxygen. It's asymmetrical, so it's going to be polar. Okay, the oxygen has a different electronegativity than carbon, so it's going to be polar. It's going to pull the electrons to one side or the other. So the CH3OH is polar, and potassium iodide is an ionic bond, so it's going to dissolve, it's going to break up into ions of potassium cation positive and an iodine anion negative, and it is going to dissolve in the polar methanol. Okay, so that's the answer to that one. Okay, factors affecting solubility on page 9. Molecular structure, so fat-soluble vitamins. Some vitamins are nonpolar, and they can, fats are also nonpolar as well. Water-soluble vitamins, there's a couple of them right there, B and C, those are polar. They will dissolve in water. Learn the terms hydrophobic, meaning afraid of water, literally afraid of water, and that means it's nonpolar. And hydrophilic, that means water-loving. Philic means loving, so that would be polar. Okay. The effect of pressure, of increasing pressure. The solubility of a gas. So now we don't just dissolve liquids and solids into a liquid such as water. We can put gas into it as well. So the solubility of a gas increases with increasing pressure. That kind of makes sense. You push the gas really hard into the liquid, and it will increase how much goes into it. That seems logical. Increasing pressure has very little effect on the solubility of liquids and solids, okay? So pressure has nothing to do with that. That's not really a factor for liquids and solids, but for gases, it definitely is. So the best example of that you're familiar with is carbonated beverages. They must be bottled at very high pressures to ensure a high concentration of carbon dioxide in the liquid. Okay, Henry's law. That's an important law in the area of solutions. What it says is the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. That really sounds logical, doesn't it? The harder you push the gas into the solution, the more that's going to go in. Henry's law is obeyed best for dilute solutions of gases that don't dissociate or react with the solvent. Okay. So the law is just a straight linear relationship, and every substance has a Henry's constant. That's the K. It depends on the solution what it is. Okay, so the partial pressure of the gaseous solute, that is whatever let's think of that as the carbon dioxide being pushed into a carbonated drink, is proportional to the pressure. How much you get into it, the concentration is proportional to the pressure. Okay, I do a little digression here. They didn't include notes on dilution. We've already done a couple of these problems in class. They're pretty easy. So let me just read this, and then we're actually going to get back to Henry's law on the next page. Dilution is when more solvent is added to reduce the concentration of a solution. So you put too much country time lemonade mix in your water, the lemonade's too strong, so the way you want to make it right is by putting more water, and you dilute it by putting more of the solvent in to the solution. If you make lemonade taste too strong, there you go. So the formula for dilution of a certain molarity is given by the formula. It's real simple. The molarity before, just think of the 1 meaning before and the 2 meaning after. The molarity before you dilute times the volume before you dilute is equal to the molarity after you dilute. That's by adding solvent times the volume after you dilute. So if you dilute 6 liters of a 4 molar solution to a concentration of 3 molar, you do that by adding, and you do the math on that, and you do that by adding 8 liters of solvent to it, okay? And it's a pretty simple relationship. Okay, so now we're on page 10, and up at the top there's a simple little problem. It's a plug and chug problem with Henry's law. So a certain soft drink is bottled so that a bottle at 25 degrees C, and that's a pretty standard temperature they're going to use for these types of solution problems. It's pretty normal room temperature, contains CO2 gas at a pressure of 5 atmospheres over the liquid. Okay, so in other words, if you look at your bottle of Coke, and that little airy space up above the liquid is at 5 atmospheres of pressure. That's 5 times normal room pressure, excuse me. Assuming that the partial pressure of the CO2 in the atmosphere is 4.0 times 10 to the minus 4 atmospheres. So that's pretty low. That's the normal atmospheric pressure of carbon dioxide, but it's much, much higher inside the bottle. Calculate the equilibrium concentrations of the CO2 in the soda bottle both before and after the bottle is open. Okay, so Henry's law states that the concentration is equal to the Henry's law constant, and they give that to us right here, times the partial pressure of the solution, above the solution. Okay. All right. So we just go ahead and plug in the numbers. Before we open the bottle, the Henry's law constant is 0.031 moles per liter atmosphere times 5 atmospheres, and atmospheres cancels. We end up with moles per liter. Remember, that's molarity. Okay, so it's how many moles per liter. So it tells us the concentration of that gas. Okay, and if we crunch the numbers on that, we will get 0.31 times 5, 0.031 times 5, and that gives us 0.155, or they round it down here to 0.16 moles per liter. Okay, that's before you open the bottle. That's the concentration inside of the soda. Now we're going to open the bottle, and everything changes. The Henry's constant for this, for CO2, stays as it was. Now, however, you're dealing only with 4 times 10 to the negative 4th atmospheres. Units still cancel the same way as they did before. Let's do that and that. Okay, so it's going to be moles per liter again. And when you multiply that, you get what they show you down here in the corner is 1.2 times 10 to the minus 5 moles per liter. So it's really the gas has spread out, in other words. It's very low, it has a very low concentration once you open the bottle, okay? In fact, it's lower than the atmospheric pressure of carbon dioxide. It spreads out. That means it's going to spread out. Okay, let's keep going. Let's read the effect of temperature, effect of increasing temperature on solubility. Okay, so in effect of increasing temperature, basically what this is saying is that generally for solids, as you increase the temperature, if it is an endothermic reaction, then the solubility will increase. In other words, if it's a reaction that wants to take in heat, then by putting in a higher temperature, giving it a higher temperature, you're going to allow it to put in the heat easier, and that'll increase the solubility of the solution. If it's an exothermic reaction that wants to let off heat, but you increase the temperature, so you're trying to kind of force heat into it, it works against the reaction, and so the reaction doesn't want to take place as well, so the solubility decreases. What else here? I'm going to skip through a lot of this. I would just say that that diagram on the right, the chart, the graphic on the right, shows those are all gases. Let me move this up a little bit here. Those are all gases. Methane, oxygen, carbon monoxide, nitrogen, helium, and it's showing, as you can see, that as you increase the temperature, the solubility of these gases decreases. It's harder to get them to go into the solvent because the molecules of the solvent become more active and they don't want to accept that gas in there. Okay, and that's, I think, pretty much all we need to have from this. Okay, so colligative properties. This is an important concept dealing with solutions. These are properties that depend on the number of dissolved particles, not on the identity of the particle. So the intermolecular forces of the solvent are interrupted whenever a solute is added. And this changes the properties of the solvent. And these properties, there's 4 of them that are affected. The vapor pressure, that's the pressure of the solvent up above, that's in gaseous form up above the liquid solvent, that becomes lower. The boiling point becomes elevated, the freezing point becomes depressed, and then osmotic pressure, that's the pressure across a membrane between a higher and lower concentration of a solute is affected as well. What this means is this: if you take these 2 reactions, you put sodium chloride, table salt, into water, you get sodium ions and chlorine ions. Okay? If you take an entirely different compound, sodium hydroxide, okay, sodium chloride you can eat, sodium hydroxide will burn your skin. Okay, it's a strong base. Okay, you end up with sodium and hydroxide ions. The only thing that colligative properties care about, they don't care anything about what these 2 substances are or what their chemical properties are. They just care about how many particles. And a particle simply is simply an atom, a molecule that stays intact, doesn't dissolve, or an ion. It's a thing, in other words, that's in the solution. So the generic term for it is just a particle. It's like thinking of like a little ball. It's just a little object there. Okay, so notice that sodium chloride, both sodium chloride and sodium hydroxide, end up producing 2 particles when they dissolve. Therefore, these 2 things, it doesn't matter what their chemical properties are, they have the same colligative properties. They have the same effect on boiling point elevation. Assuming you put the same number of moles in of each of these, it would have the same effect on vapor pressure, on boiling point elevation, that is increasing the boiling point, freezing point depression, that's lowering the freezing point, and the osmotic pressure. It's simply the number of particles, okay? And that's the whole point of colligative properties. Okay, So Raoult's law. So Raoult's law says that the pressure of a solution is equal to, there's that funny looking X again, that's the mole fraction of the solvent. So again, think of salt water in these examples. So it's what fraction of the solution in terms of moles is water. So if you have 9 moles of water and 1 mole of salt, then 9 out of 10 moles in the solution will be water. That's the mole fraction of water, is 9/10, 9 out of 10. Times the pressure of the pure solvent, that would be of the pure water. The vapor pressure of pure water is the highest. It's only when you start throwing things into it that the vapor pressure, the pressure up above the water, gets lowered. Okay, so we'll talk about that in a second. We'll talk about it now, actually. So in other words, if you have pure water, it has a particular vapor pressure. You throw salt or sodium hydroxide into it, you're going to end up with a lower pressure because the mole fraction, in the example I just gave, 9 out of 10 moles or 9/10 of the solution is water. So you multiply this by a number less than 1, 9/10, you're going to get a lower number for the solution. Okay? So let's just read what this says below. The pressure of the solution, observed vapor pressure of the solvent in solution. X is the mole fraction of the solvent. PO is the solvent. That means whenever you see that superscript or subscript 0 like that, it's really a 0. It means the initial. So it's the vapor pressure of the pure solvent. So it's the initial pressure. It's before you put any salt or other substance into it. And I is the Van Hoff factor. That's the moles of electrolyte multiplied by this. And so it's the number of particles. So the Van Hoff factor, let's skip over real quick to page 14. Okay, so right here's page 14. And let's talk about the Van Hoff factor. It's a real simple concept. It's the particles after a solute has dissolved to the number before of the dissolution. So a particle, again, is an atom, a unit cell, a molecule, an ion. So the example I gave to you earlier, sodium hydroxide forms 2 particles, the sodium ion and the hydroxide ion. Therefore, it has a Van Hoff factor of 2 because there's 2 of these for every 1 of what you had. You have 2 particles after the dissolution for every 1 particle you had before. Okay? So I gave you a couple problems where you could figure those out. What's the Van Hoff factor of NaCl? It's going to become Na, we did this one already, plus Cl minus, okay? And that's going to be 2. You're going to end up with 2 particles, whereas you had 1 there. What about H2O? H2O doesn't dissolve, so it's 1. It stays as a single water molecule. What about H2? Hydrogen, that doesn't dissolve, so it's going to have a Van Hoff factor of 2. Okay, and finally, MgO2, that's actually a typo. We're going to learn just a little bit later this week why Mg will bond with a single oxygen atom but not with O2. But anyway, those are going to break up. Okay, that's an ionic bond. So you're going to have an Mg plus and an O minus, and that's going to give you a number of 2. Actually, it's an O minus 2. It's actually an Mg2 plus and an O2 minus. To get technical, but you have 2 particles there, and that's a Van Hoff factor of 2. Okay, so now we're back from page 14 back to page 11. So we just talked about Raoult's law. So let's go ahead and keep going down below. The vapor pressure of a solution is directly proportional to the mole fraction of the solvent present. So let's make something clear about what's going on here. What you're doing, if you think of salt water, is you're throwing salt into water. Water is volatile. That means it can evaporate. Salt is non-volatile. It cannot evaporate. So of the 2 things you have in the solution, only one of them can evaporate, the water. So the water evaporates easier if it's by itself in solution than if you throw salt into the solution. And here's why. Think about the top of the water. Before you put any salt in, there were nothing but water molecules there, and water can evaporate. So every one of those water molecules had a chance to escape and to evaporate up into the vapor pressure of the water. Once you put salt in there and it dissolves into sodium, Na, and Cl ions, then they're basically taking up surface area. So that's the surface area that water molecules can have at the top of the water to evaporate, and therefore fewer water molecules evaporate. So it reduces the volatility or the ability of the water to evaporate. Okay. If the solute ionizes, the number of ions further lowers the vapor pressure. If the solute ionizes, the number of ions further affects the vapor pressure. It reduces it. That's what I just said. It's harder for the water to evaporate, and so there's less vapor pressure up above the water. The moles of solute must be multiplied by the number of ions the given solute breaks into. For instance, if we had 1 mole of NaCl as a solute, we would use 2 moles of particles for our mole fraction calculations. AlCl3 would yield a Van Hoff factor of 4 because the aluminum breaks off and each of those chlorines breaks into separate particles. So you have 4 particles. So that lowers the vapor pressure and the volatility of the water even more. For non-electrolytes, that's basically your non-metals. Those are things that cannot conduct electricity. The I equals 1. So the example I gave you back on page 14 of water or of hydrogen gas, that doesn't break up in water. So those are non-electrolytes. They don't conduct electricity. Pure water does not conduct electricity. And so it has a Van Hoff number of 1. For electrolytes, the I equals the number of particles formed when one formula unit, NaCl would be a formula unit, a unit cell, of the solute dissolves in the solvent. The experimental value of I is often less than the expected value of I because of a phenomenon called ion pairing. Especially in concentrated solutions, oppositely charged ions can pair up, and thus we have fewer particles than expected. In other words, when you put what we did in class, when you put too much salt in the water, the Na and Cl can't break up. There's not enough water molecules to break them up, so they stay together as a single particle. So you don't always have a 2 Van Hoff factor for chloride. It depends how much you put in the water. You put too much in, it'll be less than 2 because a lot of the NaCl will stay together. Okay, last sentence. Conversely, non-electrolytes, they also pair up forming dimers. Those are 2 units bound together. Okay, we won't get into that. Okay, I'm over my 30, so we're going to go through one more page here, okay? Okay, so on page 12, and I'm sorry, I got to go through page 14 today. We got to get that far today, so I'm going to push this a little bit, guys, a little bit longer than I wanted it to be. My bad, I'll try to keep these a little shorter. Okay, so up at the top, it's showing you the expected and observed values of Van Hoff factors. So sodium chloride, again, these tables are kind of photocopied from NIMSY. So you would expect sodium chloride to break into sodium and chlorine, that's a 2, but in fact, in a 0.5 mole solution, it's only 1.9. Magnesium chloride you would expect to be a 3 because a magnesium plus chlorine plus another chlorine, those 2 will break up, but it turns out to be 2.7. So in other words, the observed value of the Van Hoff factor is a little bit less than what the theoretical value is. Okay, an ideal solution is a solution that obeys Raoult's law. Okay, so in other words, when these Van Hoff factors aren't actually the values that you would expect them to be, that's not an ideal solution. There is no such thing. In very dilute solutions, Raoult's law works fairly well because you don't have the ion pairing that they're talking about, the NaCl sticking together. Solutions that are most ideal when the solute and solvent are very similar. If hydrogen bonding occurs between solute and solvent, vapor pressure is less than expected. That's because it's really hard for the volatile solvent molecule to escape from the liquid. We call this a negative deviation from Raoult's law. This can often be predicted. The enthalpy of solution formation is large and negatively, highly exothermic. Okay, I don't know why that is, but that's just a fact. You can just take that as a fact then. A great example of this negative deviation is acetone in water. Okay, fine. So here's a calculation using Raoult's law. Calculate the vapor pressure caused by the addition of 100 grams of sucrose, so that's the solute. It is a covalent bond. It is polar, but it is not ionic, so and to 1,000 grams of water if the vapor pressure of the pure water is 23.8 torr. Okay, now they're getting you into one of those other units of pressure. Remember, there's torr, there's millimeters mercury, there's pascals and kilopascals, and then there's atmosphere. So they're using torr right now. So 100 grams of sucrose. You take the molar mass, so 100 grams of sucrose would be 0.292 moles. 1,000 grams of water, take the molar mass, that would be 55.6 moles of water. We figured that one in class a few times. So the mole fraction of the water to the entire solution is the water 55.6 over the water and the sucrose added together. So water is the vast majority of that solution. It's 0.995 as a fraction of the solution. If you then multiply that by the vapor pressure of the pure water, that's the P0 in Raoult's equation, you get a pressure that's just slightly less than the pure water. It's 23.7 torr instead of 23.8 torr. Okay, on page 13, let's do these problems. These are some basic Raoult's law problems, but you got a lot of numbers to deal with here, okay? So as we read the problem, calculate the expected vapor pressure at 25 degrees C. Okay, just always, these problems are generally going to be at 25 degrees C, so that's not really an important number. For a solution prepared by dissolving 158 grams of common table sugar, sucrose, into 643.5 cubic centimeters, that's a unit we haven't dealt with yet, of water. At 25 degrees centigrade, the density of water is 0.9971 grams per cubic centimeter, and the vapor pressure is 23.76. So we know that the vapor pressure of the solution is going to equal the mole fraction of the water times the vapor pressure of the water. Okay, simple formula, but you got a lot of numbers to deal with here. Okay, so first thing we got to do is everything here is, we're dealing with mole fraction of water. So we got to take all of these grams of everything and convert it to water. So first of all, sucrose. The sucrose, it says there's 158 grams. Okay, I'm just going to abbreviate that SUC times 1 mole of sucrose for every 342.3 grams of sucrose. Okay, and if you run the number on that, what you get is you get 0.466, or excuse me, 462 moles of sucrose. Okay, now we need to convert the molar mass of water, but they make it a little complicated. We need to find out how many moles of water, but they decide to make our life a little complicated by throwing this centimeters cubed in and then telling us how the density of water, in other words, how grams, because when we need to get moles from grams, the way we always have in this class, but now we have to convert from centimeters into grams and then grams into moles. So they're trying to make life difficult for us here. Let's go ahead and do that one step at a time. So we start off, the number we know we're starting off with is 643.5 cubic centimeters. We have a density of 0.997, make those look like nines, 9971 grams per cubic centimeter. So that's going to tell us how many grams of water we have. And when we run that number, we get 641.6 grams of H2O. Now let's just keep going on the equation from here. You're going to multiply that by 1 mole, because we need to get everything in moles to do a mole fraction. 1 mole of H2O for every 18.02 grams of H2O. Okay, So then you're going to divide 641.6 divided by 18.02, and that gives you 35.61 moles of water. Okay, so the mole fraction of water is simply going to be this. It's the moles of water over the total moles of solution, which is the moles of water, plus the moles of sucrose that we figured out earlier. And that's 0.462 moles of sucrose. And that number comes out to be 0.987, and it's just a fraction. It's moles over moles. Now we're going to multiply that by the initial pressure of the water. That's this number right here. We're going to bring that down here. That's 23.76 torr of pressure. That's the initial pressure of the water times the mole fraction of the water. And that gives us 23.46 torr of pressure. And that's the answer they get down there, right there. Okay. Okay, one last problem before we call it a night. Exercise 6 on page 13. It's another Raoult's law problem. Predict the vapor pressure of solution prepared by mixing 35 grams. Okay, I'm sorry. 35.0 grams of solid sodium sulfate and with 175 grams of water. The vapor pressure of pure water, 25 degrees centigrade, that was left off for some reason. I don't know why. So let me give you that. It's 23.8 torr. Okay, all right. So again, we're just going to convert this 35 grams of NaSO4. You're going to convert that with the molar mass into moles. We have to have everything in moles for a mole fraction, and that's 142 grams. Excuse me, yeah, grams. I'm sorry, that should be grams up there as well. Okay, so we just do a little division problem. 35 divided by 142, and that gives you 0.246. Moles. Okay, now we have to do the same thing for our water. It's 175 grams of H2O times 1 mole of H2O over 18.02 grams of H2O. Sorry about the handwriting, it's getting late. Okay, and that's going to give you 175 divided by 18.02, boom, 9.71 moles of water. So the mole fraction of the water is 9.71. It's getting late, so I'm not going to put the units of measure on. Don't ever do that though. Plus the moles of the entire solution. So again, the solution is mostly water, overwhelmingly water. So this number's going to be pretty close to 1. So it's going to be 0.975. Now you're going to multiply that by the pressure that we had to look up because they didn't give it to us for some reason. And that's the pressure of water, pure water. And you multiply that. And it's 23.2. I'm just going to leave it at 23.2 torr. Okay, so in other words, by throwing sugar into the water, it's going to reduce the pressure above the water just a little bit, from 23.8 down to 23.2 torr. Okay, we'll see you tomorrow in class.